Alex, good to see you.
Warren, how are you? Look at you.
Good morning.
Grandfather Warren. Hey, guys.
Fewer grandkids than you have, though. Yeah. Just 3 on my side.
I've got a lot of catching up to do. I mean, you did more quanta than you did kids. Think of the kids as quanta, then you'll make multiple grandkids.
Yeah. But I will say that they are capable of coherently interacting when you get all 3 in the same room. It's much more than 3 times the level of disruption.
Yeah, they're very subversive, absolutely. Yeah, depending on the age. Well, if I told you my grandson, who gave me he's a sports oriented, gave me a Warriors 73 cap when I turned 73. The Warriors won 73 games in a row in 2016, I think. They lost the playoffs because of that. So the 73, my 5-year-old Matan said to me, Grandpa, you think you'll make it to 77? I said, kid, you think you'll make it to 7? At the end of that conversation. How have you been?
Doing okay. You know, I'm teaching general chemistry, and at the end of the first week of class, 10% of my students had COVID.
Wow.
And so we went virtual for a while, but now we're back live and the numbers are more manageable.
Is there an option for virtual, or do you have to come to class?
They gave me an option for virtual, but just for 2 weeks. And now we're back live.
Wow. Kind of risky for some of the kids, I think. I mean, if a kid is immunocompromised, that makes it really tough for them. We have hybrid courses. That is, it's all optional for in-person. Of course, they're recorded so that you can capture the course. You can see it later, but you can participate by Zoom as well. Yeah, the whole thing is done by Zoom, including the discussions. Hey, Bob, good morning.
Yeah, although it's interesting, I took a survey after I'd done 1 week of virtual class and 1 week of actual class, and 3/4 of them preferred the Zoom. So, because it's recorded, it's easy to go back, and it's not like there's huge personal interaction in a large lecture hall anyway.
Yeah, the thing that's tough to do is the way I teach is in these big classes is flipped. So I do these chem quizzes. They take up half the time. 25 minutes are taken up by the kids yelling at each other, basically. And that's an extraordinary learning experience. They love that. And in fact, we've shown in sort of blind studies, those taking it with and without the chem quizzes or online or just directly, that it's advantageous to have discussions. They can do that in Zoom. You can have Zoom breakout rooms where you can come in and still chat with each other, but you'd have to arrange the times so they come in at the same time. And the guy doing that is Mark Kubanek, whom you know pretty well. He's
we do that. I mean, I personally do that with the recitations, but not with the main lecture. So
you have a lot of administrative duties as well.
No, not these days. I'm no longer chair of anything. I was chair for 8 years. That's more than enough. 5 years in chemistry and 3 in physics.
Wow. You didn't do radiology? What's the matter with you?
Yeah, I'm chair of radiology. I'm not too likely to be.
I thought they were giving you tenure as chair. Which is something I'd like to do for our current chair. Is magnificent, Matt Francis. He's fantastic, fantastic chair. And so I actually instigated a vote of senior faculty to have him on, made a petition to the university for a tenured chair position. It was flatly denied. People with no imagination at all. I mean, it's like the Supreme Court. You have a lifetime appointment. We wanted Matt to have a lifetime appointment. And
so Kong, who is first?
Warren will go first.
Okay, and okay, well, are you going to introduce Warren, and then I will do Vlad? Okay, is that all right?
Sure.
Okay, can everybody see my screen?
Yeah, Warren, I think like when you share your screen, you still, I mean, part of your screen is actually blocked by the, what do you call it, a Zoom window. So
yeah, let's see if it goes away.
Yeah.
You sometimes see this happen. It didn't happen the other time, but
yeah, you see it if you share your screen instead of the PowerPoint. So if you have shared your PowerPoint, we wouldn't have seen it, I think.
hold on.
Yep. Don't worry.
That's what I thought I did though.
And we typically start like 5 minutes past 11.
Okay.
And Bob says it's the MIT time. We always start 5 minutes late, right, Bob?
It's not late, it's 5 minutes, but anyway, yeah.
Oh, we still see it.
All right. It's not going to block much of anything. So, all right. Should I just get started?
Oh yeah. I would just like do a quick introduction. So hi. But yeah. Let me just get a bit more organized because I want to show. I want to copy and paste a few things. All right. So like, good morning, good afternoon, everyone. Welcome back to our Zoom webinar again. I mean, we have taken a break because like summer break, and then like there were a couple of conferences. And in particular, I mean, I just came back from one of the and I think it's the first, almost like the first like fully in-person conference since COVID happened, Hype 21 in Lyon. It was good to see many of you. And I mean, by talking to several people, I think now hopefully we will have a better control over the pandemic situations, and maybe there will be more in-person meetings in the future. I think perhaps the next one, it could be Chamonix, which could be in person. So while I mean Bob and I, we have been thinking about like, shall we still keep this Zoom webinar or shall we do it less frequent? So this is something that we are still thinking, and hopefully we can get some feedback from from the community whether we should still keep this going. Anyway, so it's good to see you again, and we have two very good speakers today that we will share their research findings with us. So the first speaker is Warren, and actually it's interesting when he fill up his CV or his portfolio. He says that he's the 26th great son of William the Conqueror. All right, it's an honor to have him here, and he did his undergrad at Harvard University. After that, he went to Alex Pine's group at UC Berkeley to do his PhD. After that, he went on to a slightly different path. He joined X-SABRE's group in Caltech, and after that, he's now a professor at Duke University. So like, Warren is quite an interesting, he has a very interesting group because like he's one of the very few people that I know has research both in the optics and also in the NMR side. So we are now looking forward to see what he has to tell us with his latest research findings. The floor is all yours, Warren.
Okay, thank you very much. It's fun to give a talk here. Now, I realize that most of the people here are most familiar with dynamic nuclear polarization as a hyperpolarization method. And this is going to focus on one of the other methods, SABRE. But really, this is going to be as much a spin physics class as it is a hyperpolarization one. Because, the interesting thing about SABRE frequencies is you're working at microtesla and millitesla magnetic fields. And while a very small number of people, such as Alex Pines, have actually done some work at those fields over the years, for the most part, it's been bypassed by the magnetic resonance community for the obvious reason that the sensitivity is considerably lower. On the other hand, with the advent of certain hyperpolarization methods, there's the opportunity to get extremely large sensitivity by doing manipulations at microtesla and millitesla fields. And you have degrees of freedom that you don't really have in conventional NMR spectroscopy. It's not easy to completely turn off the main magnetic field or change it by a factor of 2. It's trivial to change the magnetic fields as rapidly as you care to when you're talking about microtesla and millitesla fields. And so there's a lot of places where the spin physics has been underexplored. And one of those is one that we've encountered over the course of the last several months. It turns out that the whole theoretical justification that we and others have used for rationalizing how you do SABRE isn't right, because the idea of avoided crossings or level anti-crossings, while rigorously correct in quantum mechanics, doesn't actually give you much information about optimization in systems where quantum mechanics and dynamics play competing roles. So I'm going to show you a variety of cases which are extremely non-intuitive if you think in terms of avoided crossings. One example is, I'll get to much later on. In SABRE, the optimal magnetic field for generating polarization is typically about half a microtesla. And this is a simulation, which I will validate with experiment extensively, which shows how the polarization grows in with time. And it's pretty typical kinds of numbers. You get 10 or tens of percent. You get growth in 10 seconds or so. So it has some huge advantages. And hundreds of molecules have been polarized. The sequence at the top is one that looks completely ridiculous from the standard perspective that we think about in magnetic resonance. It's 0 magnetic field for 3 milliseconds and roughly the Earth's magnetic field for 13 milliseconds. Nowhere is there anything close to an avoided crossing in this, yet it gives you 3 times more signal. And I'm going to explain how this works and how you use some changes in this to optimize practical pulse sequences. An example of the kinds of things I'm going to be showing you are looking at square wave sequences where I'll use average Hamiltonian theory and perturbation theory to give you insight, and I'll use very rigorous calculations, which are validated by experiment, to show that the insight I'm giving you is the right answer, which is that sequences which are initially non-intuitive but easily explained get you factors of 3 or 4 larger signals if you do them right in this hyperpolarization. Okay, so because not everyone here is familiar with SABRE, I'm going to do a really quick overview. You start with an organometallic catalyst. It's almost always iridium. That's that atom right there. You take parahydrogen, which is very easy to make in ton quantities, as they used to do in the space shuttle, and some target molecule. In this case, pyridine is the one that's being shown. And what happens under the right circumstances is you bind the parahydrogen into a hydride, which is a singlet, and you bind the target molecules typically along the nitrogens. And this is completely reversible. These things exchange off on a time scale of a fraction of a second. These things exchange off about 10 times faster than that. All this depends on temperature. And the miracle, what looks like at first, is that if you do this under the right circumstance, at the right magnetic field, you start with no magnetization, because the parahydrogen has no magnetization, and you convert it to magnetization pointed in one direction on the ligand and in the opposite direction on the hydrogen itself. So to understand this a little bit more, I'm going to draw this out a little bit more schematically. I've shown you in one case the 4-spin system. This is a 3-spin system, which is even a little easier. So this is looking at, for example, acetonitrile, where we're going to put a nitrogen 15 here, and normal pyridine. And again, the idea is that at the right magnetic field, the singlet state that arose from these parahydrogens can end up being converted into magnetization on a nitrogen atom. Now, this was originally demonstrated by Duckett and co-workers in 2009 with direct polarization to hydrogen, and that takes about 6.5 millitesla. And for nitrogen 15, it happens at about half a microtesla. Okay, so why does it happen at those magnetic fields? And so the standard logic that you use to explain this invokes avoided crossings. So let's do just a tiny amount of spin physics to start. I'm going to do the 3-spin system. So I'm going to look first at this system right here. It turns out that this J coupling is very large, and this J coupling is essentially 0. And so we have a Hamiltonian we can write down that just has the ligand, we'll call it L, coupled to one of the 2 spins. You have the hydride atoms, you have the resonance frequency of the nitrogen 15 in this case, but it could be carbon 13, and the resonance frequency of the protons. So that's your Hamiltonian. I can rearrange this quickly so this second line is nothing more than a rearrangement. And the first term commutes with everything else and with the final state. And so as a result, you can ignore it and you can simplify down the Hamiltonian for the whole system to this. And this is useful because the terms that are listed by different colors here, the green, the black, the red, and the blue, all play different roles in terms of actually pumping the transitions. Okay, so now, again, let's just look at this 3-spin system. So if it's got 3 spins, you've got 8 nuclear spin states. it quickly decomposes into blocks of 1, 3, 3, and 1. And the spin states that are initially overpopulated are the ones that are singlet in the hydrogen. Those are the ones that were created when you actually bound parahydrogen and those sorts. So singlet hydrogen alpha and singlet hydrogen beta are the ones that are overpopulated. Then if you just write down the Hamiltonian, you'll see that you have something that looks kind of like a two-level system right there. And as in any two-level system, you would get avoided crossings if you made these two diagonal elements equal to one another, and you would get a coupling between them. So, you know, the usual way that you write these things out, you draw one line sloping down and one line sloping up, and then you have them not actually intersect. And this is, of course, routine in quantum mechanics in many problems. But the places in quantum mechanics where avoided crossings are actually useful are things like adiabatic passage, where you actually go through them. And so a step is taken here and in many, many other problems, including some problems in DNP, where you essentially say that if you meet the avoided crossing condition, that maximizes the rate of actually generating polarization. And as I will show you, that turns out not to be the case in this system, and probably in a lot of other systems as well. In any event, the avoided crossing condition is going to be the resonance frequency difference between the proton and the nitrogen equal to the J coupling plus 1/4 of the J coupling between the hydrides and 1/4 of the J coupling away from the hydrides. Now, this is a 3-spin system. In the 4-spin system, you get 2 conditions, a little cleaner, less competition. But the evolution is very similar. Everything I'm going to show you actually works in much bigger spin systems. But just to make this a little easier, I'm going to focus on the 3-spin system. Okay, so let's take acetonitrile, an unlabeled pyridine. And when we started doing this, which was a few years after Duckett did it, Duckett had the hydride J coupling is 9 hertz. We knew from first principles what the NH coupling should be. So you could calculate it, and you would expect that this level anti-crossing field is about half a microtesla. And indeed, experimentally, these are the dots you get, and that's basically what you see. You see a maximum coming up in some place around half a microtesla. So that's good, and we were sort of off to the races in the first papers, and then off to the races in a large number of other systems that we'd explored. Turns out, though, although no one paid much attention to it at the time, several groups a few years later actually measured what the J couplings look like in these systems, and the hydride J coupling is negative. It's not positive. Now, that sounds pretty academic, but it drastically changes this numerical value right here. And so, in fact, the level anti-crossing condition is where the dotted lines are. It's a factor of 10 away from where the actual experimental best field is. Now, again, nobody paid any attention to this, particularly because we'll talk later about how you do accurate calculations, and accurate calculations hit right on the money the experimental curves. But the problem is that this level anti-crossing insight is what you'd want to use for designing new pulse sequences or understanding the underlying physics. And so what this says is the method we've used for understanding and gaining insight is way wrong. Okay, so in fact, this is a very complex system. You have your initial catalyst sitting here. It undergoes a whole bunch of exchanges which allow you to either replace the hydrogen in the hydrides or replace the individual ligands. And so this is an interesting case where the J couplings and the lifetimes are all quite comparable to one another. So the dynamics is indeed complex. And we actually did so if you ask about quantum mechanics and exchanging systems, that goes back to Redfield theory for standard relaxation. It was adapted for exchange by Binch and a bunch of others. And Redfield theory is essentially the second order master equation or perturbation theory. And sometimes you see this written out as a density matrix with an exchange term that looks like R rho, R dagger minus rho over tau. This is exactly the same thing as just written as a super operator. And this has been the formulation that we've used for 50 years for understanding how you couple exchange and quantum mechanics. But because it's only good to low order in perturbation theory, you need to use extremely tiny step sizes in order for this to converge. So my student Jake Lindale came up with a truly remarkable calculation, which got published last year in Science Advances, which shows that a trivial modification to this, change that number to this, which you calculate once, and so this adds 0 time to the calculation, makes this correct not to second order in perturbation theory, but to infinite order in perturbation theory in the exchange. And it vastly improves the radius of convergence for step sizes. So as you see, as I increase the step size with the ordinary approach to exchange, the errors grow very quickly and they grow far, far more slowly by doing this. So what this gives you is a tool to be able to calculate a very large number of spin systems more readily than you can actually do the experiments. And of course, you validate them with experiments later. So let's look at the sequence that I showed you to begin with. Let's start with something where we have 0 magnetic field, because when there's 0 magnetic field, you don't produce any net magnetization because nothing knows the difference between spin up and spin down. And then some post-magnetic field. So I told you before that experimentally, you get a maximum around half a microtesla or so. And so with a sequence like this, if you repeated it very rapidly, you would expect to see some curve which looks like this. This dotted line corresponds to an average magnetic field of about 0.6 microtesla. And you'd expect to see things fall out there. What you actually get when you calculate is something that looks very bizarre. You get these dotted lines here, which are places where you go through 2 pi worth of oscillation between the proton and the nitrogen resonance frequency. You get sharp bands on either side, and you get the signal going up as you go off in that direction. Okay, now to make this a little bit easier to see, I'm going to plot the same data, but I'm going to plot it instead of writing BD versus tau D, I'm going to put the pulse area down here on this axis. So now you can immediately see this is where you have an area of 2 pi in this between the hydrogen and the nitrogen frequency. That's 4 pi, that's 6 pi, and so forth. Okay, so something is happening which doesn't correspond at all to anything that looks like avoided crossings. And you'll also notice these curves are getting darker as you go out here. As you get to, for example, the case I showed you on the first page, you've increased your signal by about a factor of 2.5. Now, this is not just an artifact of having 0 magnetic field here. I can put a small magnetic field here. And again, you see the same basic structure, all this oscillatory stuff. And it's reasonable to ask, what on earth is going on? Okay. Now, before we do that, let's verify it's real. So this is the calculation with the 0.5 microtesla field. Here, I'm going to go across 2 lines like this. These dots are experimental data. These lines are the simulations with no adjustable parameters. So as you can see, we do in fact have a great deal of confidence in the simulations. You can see this doesn't look like a sine wave or something like that. It's got a very strong structure associated. So where's this all coming from? Well, let's take even a further step back. Let's go back to just continuous wave SABRE, the way we originally did this. And we ask what the matching condition is. And this dotted line shows you that level anti-crossing matching condition as a function of the J coupling. So you see, for a very tiny exchange, yeah, this does more or less tell you what's going on. It tells you there might be some problems, that the normal limit in which most people work with ordinary SABRE is down here and it's too low. And the normal limit in which nitrogen 15 or X-SABRE works is up here, which is a little too high. But now, if you turn on exchange, you start seeing things that are very different. There's that level anti-crossing condition. This is how you actually go through and optimize the signal. And this is not just an artifact of the 3-spin system. In the biggest spin systems we calculate, you see essentially exactly the same thing. So we need to take a step backwards and ask what's actually going on in the dynamics if we want to understand how to optimize the dynamics. Okay, so I'm going to do this 2 different ways. The first way I'm going to do it is just brute force perturbation. So this is a standard Taylor expansion for taking the initial density matrix, and there again is your Hamiltonian. And your initial state of the system is hyperpolarized on the two hydrides, and a singlet state is I1.I2. So what we want to do is we want to ask how you convert that into magnetization of the ligand, LZ. So here's where I start. This is where I want to end up. This is the tool that I'm going to use to do that. Okay, so only one of these terms does not commute with that. That's the blue term sitting right here. And so the first step has to be that one. We can work our way backwards. Again, only one of these terms does not commute with the target state. And so the last step has to be from this. And now you can connect the two in between. So you find out you need to use this coupling once, you need to use this coupling twice, and you need to use the resonance offset. So the signal appears first in the fourth derivative, and it is proportional to the square of the coupling between the hydrogen and the nitrogen times the resonance offset, the difference frequency between the protons and the nitrogen times the hydrogen. Okay, so that's a good start, but now let's think about this a little bit more. The resonance offset in this calculation is only doing one thing for you. It's doing a phase shift. It's turning, for example, Lx into Ly. It's not really acting like a frequency. It's generating a phase shift. And that turns out to be important for understanding what happens next. If you go to a very high resonance offset, you naturally quench this. If you have this unquenched, you naturally have a very low resonance offset. So in normal SABRE, you have a competition between the non-secular term in the J coupling and the resonance offset. And you try to get to some compromise field that lets you use both at the same time. Okay, well, so that gives you the first idea of how you might get better than that. So now we have a time period here where the resonance offset isn't there, which means the non-secular term is completely untruncated. And now I have a time here where I have the resonance offset truncating the J coupling. The trick is that the duration of this thing, if this is a high magnetic field, has to be not quite an integral number of cycles. It has to be over the course of the lifetime of the species, you pick up pi/2 of phase shift. And so that's where the very funny structure actually comes from. Okay? In fact, you can look at it more carefully. You see, this thing doesn't look sinusoidal at all. So it's peaked here because you go through, for example, in this pulse sequence right here, 3.575 milliseconds is much less than the lifetime of the species. You want to accumulate pi/2 over the lifetime of the species. And so that's what ends up giving you these sharp resonances. And you can get rid of inhomogeneity effects by using bipolar fields, make it positive on one side and negative on the other side. And so that's what you actually see here. Again, what I'm doing is I'm taking experiments on the dots and solid lines from the simulation. So again, we have a lot of confidence in what's actually going on. Another even simpler example is that, so the problem is if you do a field like this, where you pick up a large number of rotations during that time, the signal you get oscillates back and forth. Look at how this is going down very abruptly in this case. So right at 14, it's nothing. At 14.1 cycles, it's huge. At 13.9 cycles, it's huge, and so forth. And again, that's this function of trying to pick up this phase shift. But if I make this a bipolar field, so I keep it the same amplitude, but I have the areas not quite canceling one another, suddenly I have something that is completely independent of the amplitude here. And so this allows you to actually go to systems that are not as carefully designed for massive homogeneity as the one I'm doing all these demonstration experiments in. And again, solid lines are the simulations, the dotted lines are the experiment. Okay, so now let's try a second idea. Let's use average Hamiltonian theory in order to create new operators. And so in this case, what I'm going to do is I'm going to let this term, the non-secular part of the Hamiltonian, generate a rotation on the other terms which are actually sitting here. I'm sorry, I'm going to let this generate a rotation on this. So what I'm going to do now is this rotation here is going to take xx plus yy and convert it to xx plus yy times cosine and xy minus yx times a sine. Well, okay. So what I've now introduced is a new operator, xy minus yx, into the effective Hamiltonian of the system. So let's think about this schematically. Suppose each one of these individual pulses had an area which is equal to pi. And so it rotates you from xx to plus yy to xy minus yx to minus xx minus yy. You can see what, and this second part just traces it back over. You can see what the average is. So in this case, you produce an average Hamiltonian which looks like xy minus yx. Okay. Well, so we have under our control the ability to put another term in the Hamiltonian, and that turns out to be cool because now you actually get to magnetization in 3 couplings instead of 4. But unfortunately, the order matters. And so if you add up all the pathways, you end up not getting anything out unless you bias it. And if you bias it, have either a slight resonance offset or you have the areas not equal to one another. What happens is the effective Hamiltonian, the average over the sequence, keeps propagating forward in a specific well-defined direction. And this allows you to produce significantly more magnetization and significantly faster than you would have gotten by just doing the ordinary approach. So I'll show you a comparison of a bunch of different pulse sequences that one could think of. In each case, you bias this a little bit. So you put a DC field, which is very small, about 1/10 of a microtesla, on here, and on top of it, you superimpose a square wave, a sine wave, a chirped square wave, or a sawtooth wave. Your first guess might be, because of the high symmetry, that these would be the things you would want to use. In fact, it turns out that breaking the symmetry gets you huge advantages. These are the things that you want to use. And it's because of some mathematical terms that I can talk about in the questions, but essentially because what we want to do is to substantially decrease the average size of the coupling, because as I showed you, the average size of the coupling is too big to efficiently do this. And if you do that, you're perilously close to 0 in here, and you're not close to 0 in there. So here, for example, corresponds to looking at a square wave. And looking at a square wave, as you keep this little resonance offset constant, you keep the amplitude of 10 microtesla. And as you slightly vary the lengths of the pulse, and what you see is you get all these wild oscillations. And so with normal inhomogeneity, you would actually average over a lot of this stuff. And again, you see all of this experimentally. If I do a sine wave, it's actually worse. You get these zeros sitting in here. You want to be really close, but not exactly at that 0 in order to get your maximum signal. So you get these nasty looking oscillations here. With chirped pulses, suddenly you produce this nice, smooth, clean region where everything works well, even if you have a huge amount of inhomogeneity. And the same thing actually happens with triangles. And again, all of this we can understand qualitatively by writing down an average Hamiltonian. We can understand the basic principles of it also from perturbation theory. We can validate it with calculations that work extremely well. And then we demonstrate experimentally, typically with factors of 3 enhancements that are very robust to experimental situations. So I'll just summarize. So this has nothing to do with level anti-crossings. There are no level anti-crossings on average or on peak on most of these pulse sequences. But if you just think about it in terms of either perturbation theory or average Hamiltonian theory, you can predict it, you can optimize it, and it gives you many more opportunities to extract the useful quantities of hyperpolarization from this. So the three people who did almost all the work that I described here are Shannon, Xiaoqing, and Jake, and there are a bunch of other people in my group who contributed some pieces. These are the people who paid for it, and with that, I will turn it over to ask for any questions.
Okay. Yeah. Yep. Thanks for your very interesting talk and your presentation. And I would like to remind the attendees, like if this is your first time like logging into our session, if you have a question, just type your question in the Q&A box that you see at the bottom of your Zoom interface. And with that, I can read out your question and deliver that to Warren. Yes.
So Warren, I will, so you've done all of this on your model system. What was it?
The experiments that I showed you were on the model system, which is nitrogen-15, acetonitrile, and pyridine. But we also do plenty of experiments on, full pyridine or a huge number of other molecules, which you've seen us publish. The calculations I'm showing you, so I'm inherently here only showing you the 3-spin, but the 4-spin and the 12-spin and the 15 spins all look essentially exactly the same. Just for simplicity, I'm just showing you the 3-spin system for the purpose of this presentation.
Right. And you're so you're getting about 5 or 10% polarization in most of the cases. Is that?
It depends on the relaxation rate of the nitrogen-15 compound that you're looking at. In some cases, you get 25 or 30% polarization. Under these particular circumstances, typically things are 5 to 10% polarization. But the species that are much longer lived, for example, the diazarines that have the nitrogen-nitrogen singlet, can end up producing significantly more than that. The major difference, I would say, is between this and DNP is that the volume scaling in principle is completely different with SABRE. In principle, you can take an arbitrarily large volume with the scaling. It's just that in practice, we have been limited by our understanding of the physics. And I think that limitation is going away.
Mm-hmm.
So Art, yeah, I can say a little bit more about the infinite perturbation result. So we have actually looked at, all right, so the solution is correct to infinite order in the exchange term. It is not correct to infinite order in the quantum mechanical evolution term, which is why it's not a completely exact solution, but it drastically increases the radius of convergence. And we have extended this to a large number of other systems in all sorts of different exchange rates. It turns out to simply be that in exchange for a very tiny difference in the calculation, you end up drastically improving the radius of convergence. And so it's not just fast exchange, any limit works perfectly fine. And you can also get out of the limits where the limits that even NMR typically work in. So for example, you can use the Lindblad equations. And the Lindblad equations don't require you being near to the equilibrium state or near to the identity matrix. And you can solve for those, and you can solve for essentially as complex an exchanging system as you want at any exchange rate, and you always win.
Okay. Other questions from people? Huh? This is a very different topic, Warren. I think you've dazzled us all right.
I hope I've entertained you a little bit.
Oh, no, well, I mean, it's a very interesting, I mean, okay, here's Art says he sounds like I know my evening reading, okay? For this, yeah. So the question, I get from a lot of people with this is, I mean, the people I talk to are always interested in moving it to some sort of protein system. Have you tried any of this on a sort of a large molecule of some sort?
So I would say that our collaborators, Ed Checkmanev, Boyd Goodson, the various other people have more, and Thomas Theis, have been doing more of the working towards larger molecules. In the last year, we've been focusing on taking a step back and understanding what was wrong with the physics. In general, the issue is going to be that you need to bind, but there's an awful lot of places on a protein where you can actually bind to one of these catalysts. You need to get rid of the catalyst afterwards, but that actually technically is not all that difficult. And so really, I would say my focus has been to make sure that we're doing it right before we move on to doing it big.
Yeah, okay, all right. Well, okay, so I don't seem to, Kong, do you have any questions you would like to?
No. I mean, like it's a very, very difficult topic, but I must say that actually I've been reading about level anti-crossing lately because I also found that because like coming from NMR background with a solid state NMR and liquid state NMR, I also prefer using product operator formalism, also prefer using average Hamiltonian theory. So with that, actually we can get more insight into it. So maybe I just ask a little bit if you don't mind. So like, of course, I'm just curious if we can, of course, first of all, I know very little about SABRE and also parahydrogen. So I'm just curious, how would you incorporate if they are, how would you incorporate relaxation effect into the calculations if, I'm not sure if they are even important.
Relaxation effects?
Yeah.
So the relaxation effects are all completely incorporated into the calculation that we did there. The relaxation generally happens on a timescale that's significantly longer than the exchange or the coherent evolution timescale. But it's you write down the differential equation and you do it in exactly the same way that you would in standard standard calculations in quantum mechanics. So the relaxation effects tend to be uninteresting in the sense that they affect the overall signal, but not very much in terms of the time course of the dynamics. Okay, whereas the exchange effects and the J-coupling effects tend to have profound differences on the dynamics as it evolves.
Okay.
But yes, the relaxation is incorporated in every calculation that I showed you. Every calculation that I showed you includes what we would call the kitchen sink. And I didn't want to go into all the details here because it's published in that Science Advances paper. But the big advantage is it improves the convergence at no cost. And I think it is very general.
Yeah, I mean, the resonance conditions are very sharp. Okay, Art has another comment. Do you think other areas of spectroscopy might be making similar areas, thinking of level crossings?
So I think the answer is yes. The problem is that, level crossings are such an attractive looking picture in quantum mechanics, but the intuition that says the point of the level crossing is the point that you get your maximum signal, there's no theoretical justification for that in general. And so the calculations that we've been doing, I mentioned that you can go much broader than just infinite, than just very fast exchange. You can get into Lindblad theory. Jake has been doing calculations for optical multidimensional spectroscopy using exactly the same mathematical frameworks. And again, I think that this whole issue is that level crossings are kind of nice and intuitive and pretty, and there's a place where they rigorously give you the right answer, like adiabatic passage, but they are generally used far past that for justification, and there's no theoretical basis for doing that. And here's an explicit case where experimentally it's just wrong. It's wrong by a factor, by an order of magnitude.
Yeah. Okay. All right. Well, look, it's why don't we proceed to the next talk? All right, Warren, thank you for a really inspiring, interesting presentation. Something we should think about a hell of a lot more.